Today we start our new course on advanced transport processes. I assume that all of you have taken the basic transport processes course, and we have gone through over there. We have gone through the basics of dimensional analysis, dimensionless groups and correlations, the mechanisms of diffusion and convection, and the constitutive relations, Fourier's law for heat conduction, Fick's law for mass diffusion, and Newton's law for momentum, the diffusion or the stress. How do we use shell balances to derive the conservation equations? And we have solved it for simple cases, mostly at steady state. In this course, we will go a little bit further. We will derive general conservation equations which are applicable in any coordinate system in 3 dimensions and in time, and we will solve these for specific cases. So, let us first consider mass transport, the transport of mass due to fluid flow and the transport of mass due to molecular diffusion. If you recall, there are 2 mechanisms of transport. The flux is defined as the mass transported per unit area per unit time, okay, usually given by the symbol J and a subscript which indicates the direction in which there is the flux, in this case the Z direction. And the concentration of a constituent is the mass per unit volume with the symbol C, okay, for concentration. And there is a flux of mass due to fluid flow. For example, if I had a fluid flow, for example, in this x direction, okay, across a surface with perpendicular in the x direction, and I will call that as Ex, okay. The unit vector in the x direction is called as Ex. There is a transport of mass in the x direction, both because there is a fluid velocity in the x direction as well as because of diffusion. And in the first transport phenomena course, we had seen that the mass transported per unit area per unit time due to fluid flow, okay, that is the flux due to fluid flow, is equal to the concentration times Vx. Okay. Basically, the rationale is as follows. Okay. If I have a surface here, okay, with unit normal in the x direction, and I consider a time delta t, okay, I consider a time delta t, okay, with a fluid velocity in the x direction. Okay. In a time delta t, right, a volume, okay, of cross sectional area S and thickness Vx delta t will go from the left side of the surface to the right side of the surface. Okay. So, the volume transported is equal to S times Vx times delta t. The mass transported is the volume times the concentration. So, mass transported is equal to the concentration S Vx delta t. Therefore, the flux, which is the mass transported per unit area per unit time, is just equal to the concentration times Vx. You have to divide this by S, the surface area, and by delta t, the time interval. Okay. So, there is a concentration due to fluid flow, and there is a flux due to diffusion also. which is denoted as Jx, and we note that Jx is equal to minus d partial c by partial x is Fick's law of diffusion. That is for mass transfer. For heat transfer, the heat flux Qx is equal to minus k times partial T by partial x, where k is the thermal conductivity. Okay. Note that in this case d is the mass diffusion coefficient, okay, is the mass diffusion coefficient, and this k here is the thermal conductivity. Okay. Negative sign because mass is transported from region of higher concentration to region of lower concentration. Heat is transported from region of higher temperature to a region of lower temperature. Okay, that is the reason for this sign. And in the first course, I had also taught you that the shear stress, okay, tau xy is equal to mu into partial Vx by partial y. Okay. Tau xy is equal to mu into partial Vx by partial y. Okay. Basically, if I have a flow in the x direction and the velocity is varying in the y direction, then there is a force exerted on these two surfaces. Okay. Force per unit area is mu times partial Vx by partial y. Okay. And here tau xy is defined as force per unit area in the x direction at a surface with outward unit normal in y direction. Okay, so that is a constitutive relation. So this is called Fick's law, this one is called Fourier's law, and the thermal conductivity in this case is K, and this is called Newton's law. Okay. And the viscosity coefficient is mu. Okay. Note that Newton's law alone has a positive sign. I will come back and explain why that is so. Okay. So with this background, we will start our discussion of conservation equations. This is chapter 7 in the textbook. First section 7.1 relates to conservation equations. In Cartesian. Okay. Now the Cartesian coordinate has 3 axes in 3-dimensional space: x, y, and z. Okay. And this has perpendicular unit vectors in the 3 directions. Ex is the unit vector in the x direction, Ey is the unit vector in the y direction, and Ez is the unit vector in the z direction. These 3 have unit length, okay, and each one is perpendicular to the other one. Okay. So unit length implies that Ex dot Ex is equal to Ey dot Ey is equal to Ez dot Ez. This is equal to 1, where the dot is the dot product. Orthogonality implies that Ex dot Ey is equal to Ey dot Ez is equal to Ex dot Ez. This is equal to 0. The dot product of any 2 different unit vectors is equal to 0. how do we derive a conservation equation in this Cartesian coordinate system? Okay, so we take a differential volume whose surfaces are surfaces of constant coordinate. Okay. A surface of constant coordinate implies that the coordinate is not changing along that surface. Okay. So, we will have a surface, a differential volume with 6 surfaces, okay, of length delta y in the y direction, delta x in the x direction, delta z in the z direction. Okay. The left and right surfaces, okay, the left and the right surfaces are surfaces of constant y, because y does not change in that direction. The top and bottom are surfaces of constant z, and the front and back are surfaces of constant x. For these surfaces, we will write the mass conservation equation. Okay. So, I will magnify that differential volume here. Okay. Delta z, delta x, and this is delta y. Okay. So, surfaces of constant surface perpendicular to the x direction, surface perpendicular to the x direction are the front and the rear surfaces. Okay, they are perpendicular to the ex direction, and they have area delta y, delta z. Okay. Delta y is the displacement along the y direction, delta z is the displacement along the z direction. Then surface perpendicular to y direction has area delta x, delta z, that is the right and the left surfaces, and surface perpendicular to the z direction has area delta x, delta y, and the volume is equal to delta x, delta y, delta z. The mass conservation principle is basically that change in mass in time delta t is equal to mass in minus mass out plus any sources of mass. So, within this differential volume, for example, if we have some reaction giving rise to the component that we are studying, there is a source. If the reaction consumes the reactant, then it is a sink of mass. The source or sink is proportional to the volume itself. Okay. So, plus the, I will call it the production of mass in this differential volume. Okay. So, that is the basic principle, okay, of mass conservation. Okay. And we have to evaluate each term in this expression here. Okay. So, first change in mass in time delta t. Okay. This is equal to the total mass in this volume is the concentration times the volume itself. So, the change in mass in a time delta t will be the change in concentration times the volume. Okay. So, it is going to be equal to the concentration at x, y, z, t plus delta t minus the concentration at x, y, z, t, okay, times the volume, that is delta x, delta y, delta z. Okay. Okay. So, that is going to be the change in mass in time delta t. Next, we have to calculate the mass in and the mass out. Okay. The mass in and the mass out are at the surfaces of this differential volume. Two surfaces perpendicular to the y direction, two surfaces perpendicular to the x direction, and two perpendicular to the z direction. Mass in at the surface in a time delta t is going to be the flux times the surface area times delta t itself, because flux is defined as mass transported per unit area per unit time. Okay. So, let us look at the different components of the mass in and the mass out. Okay. So, first let us take the left surface. Okay. The left surface is at x. So, if I take the center of this volume at x, y and z, okay, the left surface is at x minus is at the location x, y minus delta y by 2, because the center is at x, y, z. Okay. The left surface is at x, y minus delta y by 2 and z. Okay. So, therefore, the mass in at x, y minus delta y by 2 comma z. Okay. This is going to be equal to the flux. Okay. Note that the flux is equal to c times the velocity plus the diffusion flux. At x, y minus delta y by 2 comma z. That is the flux. Mass in is flux times area times time. The area of the surface perpendicular to the y direction, the area of the surface is delta x times delta z. Okay. Because I have a distance delta z in the z direction and delta x in the x direction. Okay. So, the distance is delta z in the z direction and delta x in the x direction. Okay. Times the time interval delta t, because the flux is defined per unit area per unit time. Okay. So, that is the mass in. Okay. The mass out at the right surface. Okay. Right surface is at x, y plus delta y by 2 and z is equal to c v y plus j y at x, y plus delta y by 2 comma z times delta x, delta z, delta t. That is the mass out on the right surface. Similarly, you can write the mass in and the mass out at the front and back surfaces. So, the front surface is at x plus delta x by 2 y and z, okay, and the rear surface is at x, y minus delta y by 2 and z, and there is mass coming in at the rear surface and it is leaving at the front surface. Okay. So, therefore, mass in at x minus delta x by 2 y z is equal to, in this case the velocity has to be in the x direction for the fluid to cross a surface of constant x. Okay. So, you will get c v x plus j x at x minus delta x by 2 y z times the surface area perpendicular. Okay. The surface area perpendicular is this one. Okay. That is delta x times delta y times delta z. Okay. So, I get delta y, delta z, delta t, and mass out at x plus delta x by 2 y comma z is equal to C Vx plus Jx at x plus delta x by 2 y comma z delta y delta z delta t. Okay. And then we have the top and bottom surfaces. You can write it by analogy. Mass in at x y z plus delta z by 2, sorry, z minus delta z by 2. Okay. This is the bottom surface. So, I have mass coming in at the bottom surface and mass leaving at the top surface. Okay. This will be equal to C Vz plus Jz at z x y z minus delta z by 2 into the area perpendicular to the z direction is delta y delta x delta t. Okay, the area perpendicular to the z direction is delta x times delta y times time. Okay. And mass out at x y z plus delta z by 2. Okay. This is equal to C Vz plus Jz x y z plus delta z by 2 delta y delta x delta t. Okay. So, we have 3 components for the mass in, okay, at the 3 surfaces and 3 components for the mass out. Okay. Okay. That is the total mass in minus the total mass out. Okay. And finally, I have the production. Okay. Of mass within this differential volume in a time delta t. Okay. If this production is due to a reaction, for example, the rate of reaction is defined per unit volume per unit time. Okay. So, therefore, the production in this, okay, will be of the form S into delta x delta y delta z delta t. Okay. Okay. So, now I have to put all of this together. Okay. The left side is the change in mass in a time delta t. Okay. The left side is the change in mass in a time delta t. Okay. So, that change in mass in a time delta t is equal to C at x y z t plus delta t minus C at x y z t, okay, into delta x delta y delta z. Okay, that is the left side of the equation. On the right side, I have mass in. Okay, 3 contributions at x minus delta x by 2, y minus delta y by 2 and z minus delta z by 2, okay, multiplied by their respective perpendicular areas. Okay. So, this will be C Vx plus Jx at x minus delta x by 2 y z multiplied by the perpendicular area, that is delta y delta z, okay, plus in the y direction. Okay. So, this is C Vy plus Jy at y x y minus delta y by 2 comma z times delta x delta z and delta t. Okay, both have to be multiplied by delta t as well. And the third contribution, that is plus C Vz plus Jz at x y z minus delta z by 2 delta x delta y delta t. Okay. That is the total mass in. Okay. The 3 contributions shown by the blue over here to the total mass in minus the mass out. Okay. That also has 3 contributions, that is C Vx plus Jx at x plus delta x by 2 y z, delta y delta z delta t, plus C Vy plus Jy at x y plus delta y by 2 comma z times delta x delta z delta t. This is the right surface plus the top surface at x y z plus delta z by 2. Plus the production term, that is plus S delta x delta y delta z delta t. So, this is the total mass conservation equation for this differential volume. Okay. To go from this difference equation to a differential equation, we first write the mass conservation equation, divide it throughout by volume and divide it throughout by time. Okay. Divide throughout by volume and divide throughout by time. The left side, as you can see, has a volume, is multiplied by the volume. So, if I divide by volume and time, I will get C at x y z t plus delta t minus C at x y z t by delta t. Okay. On the right side, I can combine these two terms here. Okay. What is coming in and what is going out of the surfaces at constant x first. Okay. So, when I divide by volume and divide by time, you can see that this is multiplied by delta y, delta z, delta t. Therefore, when I divide by volume and divide by time, I will get C at Vx plus Jx at x minus delta x by 2 y z minus C Vx plus Jx at x plus delta x by 2 y z, the whole divided by delta x. Okay. Because note that this was multiplied by delta y, delta z, delta t. When I divide by volume and time, I get a 1 over delta x here. Okay. Plus the second term, you can write it quite easily, C Vy plus Jy at x y minus delta y by 2 z minus C Vy plus Jy at x y plus delta y by 2 z divided by delta y plus C Vz plus Jz at x y z plus delta z by 2 minus C Vz plus Jz at x y z plus delta z by 2 whole divided by delta z. Okay. Plus the source term. Note that the source term here is multiplied by delta x, delta y, delta z, delta t. So, when I divide throughout by the volume and time, I just get S. Okay. The term on the left is a partial derivative with respect to time. Note that partial derivative, you keep x, y and z a constant and vary time by a small amount delta t and take the difference. So, the left side is partial C by partial t. Okay. On the right side, I have the concentration at x minus delta x by 2 minus the concentration at x plus delta x by 2 divided by delta x. Okay. So, this is equal to minus d by dx of C Vx plus Jx. Okay. The derivative is the value of the concentration at x plus delta x by 2 minus the value at x minus delta x by 2. This is the negative of that, okay, and therefore, I have minus, okay, partial by partial x of C Vx plus Jx minus d by dy of C Vy plus Jy minus partial by partial z of C Vz plus Jz plus the source term. it is conventional to take the convective parts to the left hand side. Okay, the convective contributions you take it to the left hand side. Okay. And if you do that, you will get partial c by partial t plus partial of c v x by partial x plus partial of c v y by partial y plus partial of c v z by partial z is equal to minus partial j x by partial x minus partial j y partial y minus partial j z by partial z plus s. This equation I can write it in more compact form using vector notation. Okay. So, you know that the velocity v vector, I will use under bar for the vector velocity, is equal to v x e x plus v y e y plus v z e z. That is a vector. Okay. The vector j, the flux, is equal to j x e x plus j y j z e z. Okay. And I can also define a vector derivative, this del, okay, is equal to e x d by dx plus e y plus e z d by dz. Okay. When I write it in this notation, then the equation simplifies to partial c by partial t plus del dot, okay, a dot product between this vector operator, okay, and the velocity vector, okay, a dot product of v c is equal to minus divergence of j vector plus the source. Okay. So, this is the compact form of writing this mass conservation equation. Okay. So, I will stop here and I will continue in the next lecture. I will give you some more insights into what these operators mean, and then I will go ahead and derive the conservation equation in another coordinate system, that is the spherical coordinate system. So, we will continue this then. Thank you.